Hi, everyone. This is Judy Warner with Altium's OnTrack podcast. Welcome back. Here we are again with your friend and mine, Chris Hunrath from Insulectro, who's going to teach us about paste sintering today, which I don't know much about, but we're going to learn about it together. But before we get started, remember to hit all the typical Altium social media platforms, Facebook, LinkedIn, and Twitter. Please follow me on LinkedIn. And also remember, we are recording on YouTube as well as Podbean, and we can be found on all your favorite podcast apps. All right. So today we're going to talk about, I don't even know how to set this up entirely because I'm just as much as a student. So Chris, welcome back. Thank you again. And I know this isn't a new technology. It's just not one that has crossed my path. So tell us about what paste sintering is and what the applications are and benefits to our designers that are listening today.
Okay, so paste interconnect technology, as you mentioned, is not new. What's happened recently, though, is there's been some new material developments that make it more feasible for the circuit boards. Certainly in ceramic fired technology, powdered metals have been used to make interconnects and traces and circuits on ceramic circuit boards, but those fire at 850 plus Celsius, which would obviously destroy most PCB materials. So there's some new technologies out. Now there are different kinds of pastes that are used for interconnects. The one that we work with and the one that we promote is something from a company called Ormet. And their material is interesting because it sinters at one temperature and then it forms a new alloy with a higher melting point.
Okay, I feel like we need to back up and explain what paste interconnect technology actually is, like how it's performed, and then we can go into the material science part.
So, that's fine.
Just so I can keep up, Chris. I want to be able to keep up.
So, multi-layer PCBs, also not new. Typically, what you do is you print and etch any number of layers. You drill and then you plate. Typically, electroless copper to make the non-conductive surfaces conductive, and then you build up the thickness with electrolytic copper. Mm-hmm. And some people call it semi-additive process because you're using the electroless first as a seed layer. There are some other technologies used to make that dielectric surface conductive, and then you build up with electrolytic copper. And so that's how you link the layers in the z-axis. So if you think of classically as a circuit board of a web of foils printed and etched, forming XY connections, and then the drilled holes, whether they're laser drilled blind vias or drilled through holes, the plating links everything in the z-axis. Now, one of the challenges when you do that is you're consuming real estate in all the layers. So let's say you have a 12-layer multi-layer, relatively simple multi-layer by today's standards, but you need to connect layer 1 to layer 10. You've taken up the real estate in all the other layers. You can't route circuits in those places because there's a via in the way, unless you wanted them to connect to that via, and they're part of that net. So there's a term called any layer HDI. I don't know if you're familiar with that term, but it basically means you can put a via anywhere you want in any layer. Now, nowadays that's done typically by what we call build-up technology. So you start with a core of some sort. Again, could be double-sided, could be a multi-layer core, and then you sequentially build the layers.
Right.
And you only go one layer deep with a laser drill, sometimes two, depending on the design, but that's not true any layer. Anyway, you go one layer deep, you plate, you print and etch, and you do it again and again and again. That allows you to put vias almost anywhere you want in any layer. The downside is it's almost like building multiple circuit boards, so the cost really starts to increase. And of course, you're putting the board through multiple lamination cycles, and that has some undesirable material side effects depending on the material. Some materials can withstand 3 lamination cycles, some 6, some 10. But it is hard on the materials to go through that lamination process, over and over again.
Right.
Especially the lead-free phenolics, which are very common for lead-free assembly because they're relatively economic and they're also or economical. They also will survive lead-free assembly, but they tend to get more brittle every time they see a thermal cycle.
Right.
So that causes some issues too. So what paste interconnects allow you to do is change the sequence in which the vias are formed. So instead of laminating, drilling, and plating, you can actually drill, add the paste, and then laminate. So it changes the build sequence. And this is important both for the fabricator and the designer to understand what that means. So typically what you would do is you would take a B-stage layer of some sort. You could either drill it and paste fill it with what we call a postage stamp process, or you could pre-tack it, vacuum tack it at low temperature to a core of some sort or substrate, laser drill through the B stage, apply the paste, and then when you laminate, the paste interconnects the layers in the Z-axis.
Okay.
So you could literally take a piece of prepreg, laser drill it with a stencil or with a Mylar stencil, and I'll talk about how that works in a little bit.
Okay.
Apply the paste, remove the Mylar, laminate it between two copper foils, and now you've got interconnects inside a double-sided core.
That's cool.
So then if you print and etch that, now you've got a core with connections between the layers with no visible vias. They're all internal.
That's cool.
There's some technology around the paste, and again, we could talk about that, in a little bit. But
so how is it applied? Is it squeegeed in? How is it? Okay, so just like with a silk screen?
Yeah. Well, no screen. So what you do is you apply a 1 mil Mylar mask to the B stage, and you tack it simultaneously.
Oh, okay.
Then when you drill through the Mylar and the prepreg B stage to get down to your copper features, then you apply the paste, and the Mylar is your mask, and then you remove that just prior to lamination.
And so that stays, and it stays inside the hole. It doesn't just. I don't know. I don't know the consistency of it, but my mind was pictured it just wanting to drop out of that hole. But it must have some kind of stability.
It's a liquid. There is a tack dry. There are a number of ways to do this, but the most common method is to laser drill, apply the paste, dry the paste.
Oh.
Do it a second. Do it a second time to top it off, and then when you remove the Mylar, the liquid paste stays on top of the paste that's already been applied. Then you dry it again. Then you go to laminate.
Does it air dry, or do you have to cure it? What do you do?
You don't really cure it because it's metal powder based. So there isn't really a polymer matrix, unlike printed electronics inks, which is again another story. Mm-hmm. You would just dry off any of the carrier solvent used for the application process. Okay. It is a liquid. It is it's a paste, not a liquid, but when you drive off the solvent that's in it, which is less than 10% by weight, then it's just powdered metal.
Interesting.
And that's how it makes the connection. And so think about this, right? You've seen a lot of PCB designs. Imagine a 32-layer board, right? Which most shops can do, but it's not at the low end of technology. Imagine splitting it up to two 16-layer multilayers.
Yeah.
Right?
A lot easier.
A lot easier to build, and then you just paste them together at the end. And depending on the design, you could electrically test each half and only use the good ones, so your risk is low.
Oh, right.
Right? So there's a lot of advantages to this. Or what if you want to put together 3 16-layer multilayers, or 4? Or 18, or 4 18-layer multilayers. It's been done. Now a shop, instead of trying to build a 72-layer multi-layer, they're building 18-layer components. It's a lot more manageable.
That totally makes sense. So you explained some of the benefits, right? So of not, it's a nightmare, and we've all seen these cross sections of these crazy stack ups with all the sequential lam and drilling cycles and all of that, and also a kind of unintended consequence you can get is you can. From a performance standpoint, if you do enough of that, right, can't you get excess copper on the surface features? That's a very good point. So in other words, if you're going through many plating cycles, depending on how you break that up, and you're trying to meet a wrap requirement, that could definitely add up and make fine line etching more difficult. There's a lot of
There's some drawbacks to traditional processing, and then with an Ormet style process or a paste interconnect style process, you can eliminate some of those things. Even with an RF design, let's say you have very sensitive surface features, and
Yeah.
you don't want to plate that layer. You might want to put on the surface finish, the nickel gold,
Right.
but you don't want to put any additional copper. You want just the original vendor
Exactly.
foil copper.
Yeah.
You could do that with this paste, because you could create that as almost like a double-sided board, and then bond it to your the rest of the stack up at the very end, and you're done.
Interesting. So, I think you mentioned too there's some good signal integrity benefits. Did we cover that? I don't recall if you.
No. So one of the things that a lot of designs call for is something called back drill.
Yeah.
And you get you're familiar with that. So you do the back drilling to get rid of the unwanted copper. So again, in my earlier example, let's say you're connecting layer 1 and 10, and let's just say it's a 26 layer multi-layer. You're going to have a lot of extra copper metal in that via that you really don't need or want.
Yeah.
So common technology is to back drill down to layer 10. Now, of course, drilling to that precise location or depth, to remove the copper up to layer 10, but not beyond it, because of reliability concern, that's a bit of a challenge. So there's those issues. What you could do with the paste technology is let's just separate that board at layer 10, and not put a via on that half, that goes from layer 11 to whatever the other layer is, and you're done. You can eliminate back drilling and the parasitic effects of having that extra copper in the via. So that's another application. So there's some signal integrity benefits. There are some RF applications. There's some high layer count multi-layer applications. There's also any layer HDI applications. It really depends on how you design it and use the paste.
So if you're a designer, what kind of design considerations do you need to make kind of up front?
Okay, so you have to. So my recommendation would be is think about the design, think where it would make sense to split up the layers and provide the most design benefit. Generally speaking, we like the via to have a 1-to-1 or less aspect ratio. Now that might sound restrictive, but it's only in that one B stage layer.
Oh, okay.
So that's an important consideration. So in other words, if I have 5 mils of B stage, I would want my via to be 5 mils or larger where I'm going to apply the paste. That has to do more with the paste physics and how it fills the via. And then of course the receptor pad that you're putting the laser drilled via on, needs to be a sufficient size where the paste doesn't have the opportunity to run on one side or the other of the pad. So we do like an annular ring around the via. That's going to have a lot to do with how well you can register your laser drilling. Usually that's pretty good. The other consideration is the B stage you use. Spread glass is, bringing up spread glass again, but
Yep.
Spread glass is good because it tends to keep the paste corralled, whereas if you have an open weave and that prepreg resin's melting and flowing during the lamination cycle, the paste could run to that area. So spread glass is better. Higher viscosity resins tend to be better. We like low flow prepregs. So those are some of the design considerations. Other design consideration is, and I've seen this happen before, where if you have a ground area and you're making a lot of paste interconnects along a wide track, you don't want to put the paste interconnect to the edge of the track, because what ends up happening is during lamination, the resin wants to flow off the surface of the track down the sides to fill. Right, it's a hydraulic effect, and it's going to move the paste with it. And I've seen vias actually move during lamination. So just some common sense things, keeping in mind that it's a B stage where your interconnect is. You want to make sure you put that in some good locations. And in that particular case, all they had to do was go back and shift the vias a little bit to one side, and everything was fine. So it's just those kinds of things. And certainly, they could contact us. We can give them some design hints, and I can give you some literature to go along with this video or podcast.
Yeah, very good. Yeah. What's Ormet and this paste sintering's been around for a little while. What's been the sort of acceptance of it industry wide? Is it being widely accepted? Is it just on certain applications?
It's been around a long time. It was primarily used for quick turn microvia work, and also large format boards where you're literally stitching very large boards together. So you can, again, the idea is you can make boards that are nearly finished and then electrically interconnect them. The nice thing about the Ormet paste is it doesn't melt at reflow assembly. So
it changes chemically, right? So once the sintering is done, then it doesn't change, right? Then it doesn't morph and heat.
What attracted us to this technology over some other paste interconnects, because there's other processes where you would apply a paste of some sort and then make a connection with pressure in the z-axis. What interested us in the Ormet material is the paste melts at one temperature and alloys. So the paste is basically copper particles with a tin alloy powder. When the tin alloy powder melts, and the melting starts at about 130 Celsius, it starts reacting with the copper and forms an alloy with the copper instead. What's interesting about the Ormet material is it's alloying with the interlayer coppers as well on the PCB layers. So you have a metallurgical joint, not just a pressure or contact connection.
I see.
So it's unlike the tin lead or lead-free alloys and solder, the new melting point when it forms an alloy with copper is one phase is 415, the other is 630 Celsius. So it's not going to remelt at assembly. So it's a permanent connection. So really, the paste has applications for other technologies like flip chip and whatnot packages, where if you didn't want to have a secondary if you have a secondary reflow operation, you didn't want to have any more remelt. It has some applications there. Or downhole assembly is another application where the board might be subjected to temperatures near the solder melting point. It's another good application for this material. So that's what interests us, because when a board's in use, it heats up. You have some z-axis expansion. With other types of paste interconnects, you have a resistance change every time the board is heated, even from let's say 40, 50, 60 Celsius in normal use, not even in any kind of environment.
Right.
Parts of the board would heat up from the components, and you'd have a change in resistance. And that's what this is designed to circumvent, because it forms that metallurgical bond with the copper interlayers.
Interesting.
So, so it is a different technology than the paste you would use in printed electronics.
Okay. Well, that's been fascinating. Again, I feel like a newcomer to old technology, and I've known about Ormet that I think got acquired by Merck now, but I've just never had someone sit down and explain it to me. So thank you for doing that. And I wasn't
90 layer multilayers. People are doing 90 layer multilayers with paste interconnect. Yeah. Yep.
That's crazy. I didn't even know a 90 layer board existed, I guess.
Yeah, and again,
I've only really seen them up into the 60s, I guess, personally. So.
Yeah, one common design was a 72-layer multi-layer. Again, made out of 18-layer components. And one of the things with the chip test, the ATE companies, they build some high layer count multi-layers, and you need a lot of IOs. There's a trend to go to wafer level testing, where you're testing the entire wafer. You need lots of interconnects, and that's one way to get there, is to use the Ormet paste to put in lots of layers. So we're seeing more interest in it lately, and I think that's one of the reasons why the technology hasn't taken off until now, is because there just wasn't the demand.
Right. It's kind of ahead of its time, maybe a little bit, or yeah. Well, I know you shared with me some cross sections, or I think you did, and so please be sure to share those with us, and we'll put those up on our website, and we can share your website and Ormet or Merck's website, so the designers can get more information. Is there any place else besides your two websites that you would recommend for more information?
I know I've mentioned HD Pug in the past.
Yeah. Mm-hmm.
They're actually contracting some PCB manufacturers to make some HDI test vehicles
Okay.
with paste interconnects. So there's
Okay.
going to be some data. Anybody who's an HD Pug member will have some access to some really good reliability data, and they're pretty complex boards.
Okay.
So it'll really push the technology. But for breaking up, big, thick, and ugly PCBs, that's pretty well established.
Yeah. Very cool. Okay. Well, thank you. So
You're welcome.
tell us about that fish on the wall behind you.
So it was a gift from my sister. Actually, it's made from recycled materials. So there's an old PCB cut up on there, the old spark plug wire, and a few other odds and ends. Some artist put together. I actually bought it on I didn't buy it. My sister bought it on Catalina Island, and somehow we went out there as a family trip, and somehow she smuggled it off the island and gave it to me just before she headed back to Virginia. So it was kind of cool.
Oh, that's fun. It's a good throwback to your diver self.
Yeah. So yeah, just the last thing on Ormet is paste don't plate.
Is that their tagline, or is that yours?
Actually, that's their tagline. We were sharing at one of the IPC shows. But another nice benefit to the Ormet, which I didn't mention earlier, is there's no electrolysis, there's no plating processes in these interconnect layers, so it circumvents all that.
Which is like bizarre for me to think about, but
yeah. But if you're capacity constrained,
yeah.
plating, that's another benefit. So
yeah. Well, thanks again. This has been really good. If you have anything else juicy to share with the listeners, just email it over before we get this one up.
Okay.
And thanks again for this one. Now, I know we've talked about exploring down the road a little bit on copper foil integrity issues and also printed electronics. So I'm sure I'll hit you up again soon, Chris.
Yeah, definitely. I would like to talk about some of the material science behind printed electronics. And I know you guys are working on some new design tools.
Mm-hmm.
And printed electronics, there are a lot of different ways to use that in electronics. Well, I should back up. There's a lot of different ways to use conductive inks in electronics.
Yeah.
And there are so many different versions of the inks.
Which is another subject I know nothing about, so it'll be good. I'll be a student with our listeners, and I know they're out there. I know what conductive inks are, but as far as all the applications, all the different materials available, because that just seems like something that's in writing a lot that people are really turning towards as solutions.
A lot of new technologies coming out in that space, and it's going to be fun to watch as that evolves.
Yeah.
So,
yeah. It will be. Okay, Chris, thanks for another good podcast, and we'll see you soon.
Thanks for having me.
My pleasure. Again, this has been Judy Warner with the OnTrack podcast and Chris Hunrath from Insulectro. We'll see you next time. Until then, always stay on track.